Up until this point, particularly with the last bit that we've just done, we've written the equations to calculate the new position and quaternion for objects.
No.
And we can do basic 3D physics using that, and you can program something like a flight simulator, or some elements of a flight simulator, obviously not taking like wind and all the rest of that other stuff into consideration, but you can make things move around in 3D space using those equations, right? At some point, your program becomes kind of complicated, and you're either going to do like Simon's doing and write a physics engine for your project, or you can use a pre-existing one. Because there's loads of stuff that we're currently not doing in the physics in BGE. So the number one thing that we're currently not doing, what's the number one thing we're currently not doing that physics engines need to do? Just by doing those simple equations, we can move things around. What am I not doing?
Object interactions.
So object interactions. What do we call those?
Collision detection.
Collisions. The other thing is you'll discover using that form of integration, that's called an Euler integrator, okay, or the Hamiltonian method of doing integration, which is using the quaternion as well, right? But we'll discover that our simulation is going to lose accuracy very, very quickly and won't be very stable. And that's because of, I guess, the time delta, right? So there is a better way of doing the integration, and it's called, I think it's called a Runge-Kutta integrator. And it was developed quite a long time ago. It's a mathematical method of doing that integration, which is more accurate. And I think what it involves is taking a number of time steps for every big time step. Like if you have like 1/60th of a second, if you take a number of subdivisions of that 1/60th of a second, then you do some kind of crazy way of doing all your integrations, and it involves multiplying everything by a huge big matrix. I don't really know how it works, okay? But if you were to do really a physics engine, like Simon over there, maybe will give us a talk about the Runge-Kutta integrator later on in the course, okay? But for now, that's one thing that BGE doesn't do. It just does the Euler integrator, and it doesn't do collisions. So from now on, we're going to use a physics engine. And as you might imagine, right, integrating a physics engine into BGE, or BGE in particular, okay, we'll put the physics code in there, but for every rigid body like this, or for everything that I want to create, I'm going to get something else to control its position and its quaternion, and that thing is going to be the physics engine. So for everything that I make like this in the scene, I'm going to make another thing, which is called a physics controller. And the physics controller is the thing which is basically the bridge between, the game objects in BGE and one of the physics engine over here. So one kind of common thing that game engines do is you have at least two representations of everything in your scene. So you're going to have one representation which is stored in your game engine. You've got one other representation which is stored in the physics engine. And the physics engine representation might even be a simpler representation. So I could have some really complicated character model like this, and over here in the physics engine it's represented as a box like this. You know what I mean? That's quite a common thing that game engines and physics engines do. Yeah, there's a great book, by the way, if anybody's looking for a great book on all the graphics for 3D maths and things like that. Unfortunately, it doesn't do physics, rather annoying. So this is what physics engines do, rigid body dynamics. Why do we call them rigid bodies?
They don't change shape.
They don't change shape. Okay, so rigid bodies are obviously an approximation of things in the real world. There's nothing really rigid in the real world. Like if I apply enough force to that table, what will happen to the table? It will break. Okay, rigid bodies in physics engines never break. No matter how much force you apply to them, they will never deform. And that's just because they're not real objects at all. They're only just a few equations, right? And then you're just doing some integration. They also do collision detection of either geometric primitives or things called trimeshes. And these are sort of generic concepts of physics engines. Geometric primitives are shapes that can be represented by a single equation. So to give you an example of a geometric primitive, like that's a geometric primitive. That's a circle. The equation for a circle is what? What's the equation for a circle? What does an equation for a circle even mean? It tells you whether points are on the circle or not, and you can use the equation to generate points on the circle. Why would I represent that circle as an equation?
X squared, y squared.
Yeah, x squared plus y squared equals 4 squared. So that's, that's the equation for a circle, right? Every point that satisfies that circle will satisfy that equation. You know, if I pick any point on the outside of that circle, and if I square it and I add it to the y, and if it's not equal to r squared, then it's not on that circle. And that obviously applies for circles where the origin is where? 0. Okay, if the origin was not 0, then it would just be simply x minus cx to be squared plus y minus cy to be squared is equal to r squared, where c is just the center x, and that's the equation for a circle. The equation for a sphere is just x squared plus y squared plus z squared is equal to r squared. Right? So that's a geometric primitive. Another geometric primitive is a plane. We haven't really talked too much about planes, but we definitely need to talk about planes. Planes are awesome. You can do lots of really cool things with planes. The same way you can use vector dot product and cross product, you can do things with planes. The equation for a plane is ax plus by plus cz plus d is equals to 0. That's the equation for a plane. So certain things can be represented by those types of equations. And when things can be represented by these types of equations, they can be simulated really quickly. Because you can easily, for example, if my world was just full of geometric primitives, I can use just two equations and I can check to see are those, it's very easy to check to see are those objects overlapping and stuff, right? So geometric primitives, similarly there's equations for stuff like cones and things like that. You can calculate points on cones based on a simple equation, right? They also do trimeshes. So trimeshes are much more complicated to simulate because trimeshes are basically meshes composed of lots of triangles. And things that are composed of lots of triangles are much more difficult and require much more CPU time to process because obviously you've got to check to see, if I'm checking the collision between two things that are composed of triangles, I have to check to see does any triangle from here overlap with any triangle from here. And it's a much more complicated situation. And obviously they do things like put bounding boxes around objects, so you don't check every triangle against every other triangle in the scene. But that's what physics engines do, okay? Physics engines also do soft body dynamics. You know what? I should really have a look and see if I have some physics engines examples. I think I have a couple here. And they do stuff like fluid dynamics as well. And then they're also real time. So they sacrifice accuracy for speed. Okay? Does anybody notice? Some of the major players. So for 3D physics, you have Bullet Physics Library, Havoc, obviously an Irish company. Open Dynamics Engine is the engine that I used to use on this course, and I switched using it a few years back because it seemed not to be updated. And so then I just figured when I was redoing the course like 2 years ago, I picked Bullet Physics Engine because it seemed to have lots of support and was in lots of commercial engines. Box 2D, what's the big game that uses Box 2D? Millions of what? Angry Birds. So that's a 2D physics engine. PhysX is an NVIDIA physics engine. It used to be a separately owned company in physics. NVIDIA bought it. At one stage you could buy a PhysX card and plug it into your PC. This is like about 5 years ago, which is basically a card to simulate physics a lot faster. But PhysX is the physics engine used by a lot of game engines. So for example, Unity uses PhysX. I'm not sure, probably Unreal probably does, I'm not too sure. Or maybe it allows you to plug in a different physics engine. BPOO is a really cool C# physics engine that I used to use when we used to teach X and A. It's a lovely physics engine. So the Bullet Physics Engine is the one that I currently use, and it's used in lots of open source games and lots of movies as well. So for example, it's the physics engine in GTA 5. Also lots of movies use it, including How to Tame Your Dragon. The 3D Mark thing uses it, and lots of movies use the Bullet Physics Engine as well, and loads of mobile games and everything. So it's really a very current, very supported version, a very supported physics engine. It's 100% free and open source, that's another reason why I use it. Does all of the things that we might want. An interesting thing about Bullet, right? And up until Bullet 2, all of the physics was done on the CPU. But with Bullet 3, they've introduced GPU physics. So in other words, shader physics. And that enables you to simulate a lot more rigid bodies because it can do lots of the calculations concurrently in real time on the GPU. And I don't know if you have to just use the same old APIs or if you have to rewrite the program. I'm not 100% sure about that. One thing you guys have probably noticed as well is that performance of the Bullet Physics Engine is really poor if you compile in debug mode in Visual Studio. Right? It doesn't matter how fast your PC is, you need to compile in release mode to do these kind of physics things. Otherwise, you'll only be able to simulate maybe 10, maybe even 5 rigid bodies. Okay? So to use Bullet, first of all, you hash include that library, and you have to link with those 3 lib files. In previous versions of this course, you had to compile Bullet from sources. But over the summer, I did all of the compiling from sources, and now when you get BGE and the dependencies, you just have to, you do those bin files, they're pre-compiled, okay? But like I say, when you go to download Bullet from the Bullet website, you get all the sources and you have to compile it from sources, okay? So, that's what Bullet does. Yeah, so again, this is stuff that you used to have to do whenever you made a game, but now I've put all this into the base game class in BGE, and so you don't need to do this anymore. And this is what we call boilerplate code. So almost every project that you want with Bullet is going to start out by doing all of this sort of stuff. I'm not even sure what half of it does, right? But you need to put it in. So the first line, default configuration, not really too sure what that does. The collision dispatcher, not really too sure what that does either. These two parameters here control the limits of the scene. All right, so obviously -1,000, -1,000. So that just says don't simulate anything outside of these bounds. And then when you create this broad phase collision detection algorithm, you pass in those parameters. And yeah. Now, one thing that is kind of important that you need to keep track of is this object here, which is of type BT discrete dynamics world. Okay, and this is actually a field in game. You guys maybe should just write that down. Whenever you're creating a physics object, like I say, you need to create a version of it that's in BGE and a version of it in Bullet. When you create the version that's in Bullet engine, you need to add it to this thing here, and there's an API to add it. And this basically adds it to the list of things that Bullet is going to simulate. Right, so you create your rigid body in Bullet, and you add it to this dynamics world object, which is a field in the game class, and then Bullet will simulate it. Okay? And here, for example, is one of the APIs on the dynamics world is set gravity. And this just applies gravity acceleration to everything in your scene. So you could just call dynamics world set gravity. If you don't want to have gravity, just set it to be the vector 0, 0, 0. Otherwise, you can set the gravity. So that's all the initialization code for Bullet. Like I say, I haven't a clue what most of it does, but it's not too important. Yeah, so these are rigid bodies. Rigid bodies, number one, never deform. They have some things that never change. So things that never change are the object's mass, because it never deforms, right? So its mass is never going to change. These are constant. When you create this, you set its mass, and you set its inertial tensor. The inertial tensor gets calculated for you. But its inertial tensor obviously never changes. And then things that do change over time, so the position, obviously, the linear velocity, the orientation, the angular velocity, they're things that are going to change over time. And then these things get calculated, the force accumulator, the torque accumulator, acceleration. And, you can obviously add forces and you can add torque to the rigid body. And I'll show you how all this works in BGE. And we'll look at some of the code for making rigid bodies. We'll use Visual Studio to debug it. When you're making rigid bodies in Bullet, there are three types of rigid bodies you can make. Type number one is called a dynamic rigid body. And a dynamic rigid body is basically any old rigid body that things can interact with. And that will respond to other things in the scene. So for example, if you wanted to have like a barrel in your scene that could explode, that has mass, and that's an example of a dynamic rigid body. Okay, so anything that can interact with and that you can interact with. It has a positive mass, and every frame its new position in quaternion is going to get calculated based on what forces are applied to the object. The second type of rigid body you can make is called a static rigid body. A static rigid body is something like I'm sure you've all played computer games where you can walk up as far as, for example, a wall, okay, and things will hit off the wall, but the wall itself never moves. Do you follow? So things that are part of the scene that never move, but that physics objects can interact with, they're called static objects. And how you make a static object is you set its mass to be 0. Right? So something with a mass of 0 will never have its position in quaternion updated, but other objects can bounce off it. The third type of rigid body you can make is called a kinematic rigid body. And a kinematic rigid body, an example of this would be the player. So, when you make a kinematic rigid body, I want to be able to walk up to things in the scene as a player, and I want to hit off them, but my position is being controlled by a game controller. My position is not being controlled by the physics engine, and that's an example of a kinematic rigid body. Does everybody understand that? So for example, if I'm using a Kinect to make a Kinect skeleton for myself to play with in the scene, so I am the Kinect skeleton, right? I can go up and kick something. If something hits off me, what's going to happen? Nothing. The thing's going to bounce off me, but I'm not going to bounce, because something's hit off me. You understand it's controlled by the player as opposed to controlled by the physics engine, but yet it can interact with things in the scene. So everybody, can you kind of get the idea of the three types of rigid bodies? And that's how you make them, right? A dynamic body, you just set it positive mass. Static, you set it to have zero mass. Kinematic, you set it to have zero mass. And then there's a couple of little APIs that you implement to control its position and quaternion.
Is it easy enough to change? Well, I presume like you could change a kinematic body like the player to something dynamic. Because like in a lot of games, if something like a classic example is Skyrim, when one of the giants smacks you, fly off into the air into like a ragdoll. I presume that changes from.
Yeah, that's an example of something changing from a dynamic object to a kinematic object.
It's easy enough to change the two, or would we?
Yeah, I'm pretty sure you can switch between the different types. So I'm not 100% sure if you can. Sometimes maybe just the object gets removed from the scene and gets replaced with an object of a different type.
Oh, okay.
I know that like with Bullet, there's kind of weird things to do with like, whether objects can change between types and not and stuff like that. I'm not sure if always it's possible. So, okay, next of all, let's get Visual Studio open. If you guys have Visual Studio there, right? Take a look at a class called the Physics Factory. So the Physics Factory is a field in game. So when you create a subclass of game, you get an instance of Physics Factory, and it's my code, right? So my code for Physics Factory is just code that looks after, the construction of a body in Bullet and the equivalent thing in the Bullet physics. Sorry, the thing in BGE. And the equivalent thing in the Bullet engine to keep track of everything. I'll show you how it looks like, right? So let's take a look at an engine, Physics Factory. If you guys have a PC, you can have a look at the code in your PC. And let's take a look at a simple example for create box. And you can see how the object gets created. See that up there? So a lot of this is, I would say, kind of boilerplate type code that you just, a lot of this I figured out by looking at the examples, okay? So these are the steps involved in creating a rigid body in Bullet. You can use the Physics Factory just to create boxes. If you want to just in your assignment, for example, just use the geometric primitives that the Physics Factory exposes, that's fine, alright? But you do need to know the steps involved and what happens inside the Physics Factory. So, these are the steps. First things first, BT collision shape. So this is the shape that's going to be used by the Bullet physics engine for collisions. So you first of all make a BT collision shape, and it's an ordinary pointer, it's not a shared pointer, okay? And the parameters that it takes an example, it takes a BT vector 3 object, and it takes the width, the height, and the depth. Now, why do I multiply by 0.5 there?
Half the size.
Yeah, no, it's obviously getting half the size. Now, I guess I must have just figured out that my box is a unit one. Not quite sure why you have to multiply by 0.1. It's obviously why you have to do it, and that's because the width, the height, and the depth. Hang on, I know why. If you look up the API for this, the API for this, rather amazingly and strangely, look at this. The constructor says half extents. Alright? So you pass in half the extents of the object. That's what it takes. I don't know why Bullet takes half the extents. So that's why you have to pass it. This BT vector 3, you multiply it by 0.5, you give it half the size. I don't know why. That's the way the Bullet API is implemented. Is that okay? So, the next thing, I have a scalar here, which is the mass of the object. The mass of the object is either going to be, standard mass, I think, I make everything is 1, okay? But if the object is kinematic, are you guys familiar with this syntax in C?
No.
So look at this, what does this mean? Kinematic here is what? No, but it does look like a cast. Yeah, so, I can totally see why you think that is a cast. It doesn't actually matter, the brackets are actually not important. So what do you think, what's the type of kinematic?
Binary.
It's a Bool. It's a bool. Okay, so this is a parameter that's passed into this thing, and this is a bool. So if this is true, wait, what this works? This is kind of not really. You guys might remember this. If you see this thing here, A equals. Let's just say A equals. Let me just go B, C, D. Okay, so this is C. Have you guys seen this way of doing an if statement before in C? Who hasn't seen it before? Okay, so you can write this down. Okay, what this basically means is it will evaluate this thing before the question mark. If this evaluates to true, A takes the value of C. If this evaluates to false, A will take the value of D. Right, so maybe just write a note on that. That's just a thing that you'll see sometimes it works in Java or C# or C. It's just a way of doing an if statement really quickly. Is that alright with you, Connor? Figure it out. You familiar with this, yeah? Yeah, cool. So if the object is kinematic, so Boolean flags passed in, I set the mass to be 0. Otherwise, the mass is equal to standard mass, which I think I set to be 1. Okay, and it's a scalar. BT scalar just is predefined to be a float, but I think it can also be a double if you want double precision. So then I need to make this inertial tensor for the object, and then the next step is the inertial tensor. I guess when you're making an inertial tensor, it sets it up to be a vector 3, because I'm only interested in the 3 numbers across the diagonal. So that's why it's not a matrix 3. That's why it's a vector 3 as opposed to a matrix 3. So then you have to say, this is the shape of the object, and then you go calculate local inertial tensor. You say what the mass is, you pass in this guy here, and there's an interesting thing. What gets returned? Like, how is that calculating the local inertial tensor? This is basically a C++ thing. You might really realize this. You might wonder, like, how is that calculating and returning? So, again, it's helpful if you guys maybe take a few notes just so you understand what this code is doing. If you look at the parameters for this, it's not a pointer. Look at the API here. This is the API. I'm going to bring it up. Calculate local inertial tensor. First parameter is just a BT scalar, which is a float. Second parameter, BT vector 3 ampersand inertia. Does anybody know what that means? Huh? It's actually a thing in C++ called pass by reference. So do you remember, you guys did C# in second year, didn't you? Do you remember pass by reference? There's a couple of keywords in C# for going pass by reference. That means that the parameter here can be changed, but you don't have to pass it as a pointer. It's a C++ thing. When you have this ampersand here, it means that this BT vector 3 is passed by reference. So this method, this API call here, is going to fill out the 3 values in this inertia vector 3. And that's how it gets passed by, because it's passed by reference. Does everybody understand what passed by reference means? It means that the object is passed in as if it was a local variable to this, or as if it was basically in the same scope as this method. That's actually how it works in C++. It's called pass by reference. Essentially, it just means that the values held in this thing can be changed. Alrighty? So then I calculate the inertial tensor using that API call. Now, this is just like a BGE API call here. So I make shared, a thing called a box, and you pass in the width and the height and the depth. What do you think this box object is? It's a prefab in BGE. What do you think it is? I mean, just understanding what you know about like how BGE works. Somehow or other, it's going to have vertices in there for a box. Yeah. What do you think it is in terms of components? What components are required to make the box?
Transform.
Sure. So the transform isn't really a component, right? So I'm going to have basically 2 objects, 2 components. One which is something with a transform, and attached to it is going to be a model of a box. So what you get back is you get back something with a box model attached. Alright, so it will go and load a 3D model of a box and attach it to a game component, and that's what you get when you get this prefab thing here. Okay, so that basically is the rendering thing, and that's the thing I'm going to add to the list of children in BGE. Now, the next important thing here is this parameter here. And this parameter here is how I set the initial orientation and the initial position of the object. Alright, so I make this thing which is called a BT default motion state, and I pass in the quaternion, which gets passed into this guy. So this is the initial quaternion for the object, and I also pass in the initial position, and I get this BT motion state thing. And then another API call you need to do with Bullet. When you're constructing a rigid body, you pass in a BT rigid body construction info object, passing in the mass, which is the scalar, the motion state, which is the initial position on quaternion. You pass in the shape, which is going to be used for collision detections, and you pass in the inertial tensor. So that gets you a construction info thing. The final step then is, in fact, that isn't even the final step. There's loads more steps. This is C++, guys. This is, you want to be C++ games programmer, you get lots of code. So then you make this BT rigid body object. This BT rigid body object, tell me what you think we're going to do with that object. You might recall, we mentioned it a couple of minutes ago.
That's a world.
Awesome. That's the thing that gets added to the world. So after doing all of those different steps with Bullet, I end up with this body, which is a BT rigid body object. Later on here you see I am adding it to the dynamic world. And then that basically just tells Bullet to go and simulate it. Now, there's quite an important step that we have missed out on, okay? And the important step that we've missed out on, I've made that box thing up there, which is basically, a game component with a model attached. And now I have made this BT rigid body object, which is the Bullet equivalent of that object. I need something which every update goes and asks Bullet for the new position and the new quaternion of that object, and sets that on the box, so that the box's position and quaternion is controlled by Bullet. You follow? That's the bit that's missing. The thing that links those two things up together, I call a physics component. What do I call it? Physics controller. So the last thing I do is I make this thing called a physics controller. The physics controller is just a thing which gets added to the box that I previously made, and it also has a reference to the Bullet rigid body. Okay, so you make the physics controller, then you attach that to the box that I previously made, and what that has is that knows the Bullet physics object, and then because it's attached to the box, it can be used each frame. Each frame, what this physics controller is going to do is it's going to go to the rigid body object in Bullet, get the object's position, get the object's quaternion, and update the thing that it's attached to based on the position and quaternion. So does that make sense? Right, let's run it in the debugger. There's loads of what I would call boilerplate code there. In other words, every time you need to make a rigid body in Bullet, it's pretty much the same thing. For cylinders, it's a different thing that you're making and a different set of parameters. For tri-meshes, it's completely different, because for a tri-mesh you have to actually go through the triangles in the object and create all those triangles inside some Bullet object. But let's take a look at this, right? I'm gonna run this in the debugger here, and I'm gonna open up. If you guys have the code there in front of you, you can have a look at this. So the first thing I'm going to do is I'm going to open up Physics Game 1. Physics Game 1. So here's Physics Game 1, okay? And what I'm going to do Physics Game 1 is I'm going to comment out most of the code. Okay, so let's get rid of the video graph here again, and here's my physics factory. You know what, just before we'll finish this example, okay? In fact, you know what, let me stop the debug here for a second. There's one very small change I want to make to this, because the identity quaternion is fun. But it's more interesting if, instead of using the identity quaternion, let's set this thing to have a 90-degree rotation around the x-axis. So I can just see how that quaternion kind of passes through the physics engine, from BGE to the physics engine, from the physics engine back to BGE. So, how would I make a 90-degree rotation around the x-axis for that parameter there, for that quaternion? What's the API call I use to make quaternions, do you remember? Huh? You guys know it. I know you do. Yep. So we need an angle and an axis. This is a was slightly confusing me for a while. I thought everything was broken, but then of course I realized that, let's go, GLM quat Q equals GLM axis, angle axis. So, next question, radians or degrees? Degrees, yeah. This is why I thought BGE was broken, because I was passing in the parameters radians. Of course, it should be degrees.
Does it tell you in the type there?
Huh?
Does it tell you in the type pop-up?
No, it just says angle. You need to look up, like Google it, and you'll find that it's actually degrees rather than radians. So that gives you it in degrees. The second parameter is the axis of rotation, which is GLM vec 3 around the x-axis, so 1, 0, 0. So that just means the box should be rotated 90 degrees around the x-axis. It should be flat, right? It should be flat. Let's just make sure that it's flat. Oh, of course, I need to pass that in. Function F9. Over in physics grade 1. Let's pass in Q there instead. Let's run it. So just make sure we get a flat box now. Rotate it 90 degrees around the x-axis. There we go. So we get a flat box, right? So that's its initial quaternion. Right. Let's have a look at physics factory. Set our breakpoint here and just see how those values get passed in and out of the various different components. Okay, so now when you look at quat, it's interesting, right? Let's look at the quaternion now. It's a 90-degree rotation around the x-axis. It doesn't really matter. In actual fact, the W component is equals to, is it the sine? The x, y, and z are equals to, you need to look it up. I can't quite remember how they're calculated. It's not too important, but, you know, anyway, the x component is 0.7, the w component is equals to 0.7, and the y and the z are both equals to 0. So let's just remember those numbers, okay? So that's the x is equals to that, the w is equals to that, the y is equals to 0, and the z is equals to 0 as well. Let's remember that as being the quaternion. That's the object's quaternion, okay? And I can't remember how the quaternion is calculated. You can look it up. I'm sure I have it in the notes somewhere. Like it's the sine theta over 2. Do you remember it, Simon? I can't remember. You look it up anyway, right? And you'll find that there's a little formula for calculating the x, y, and z components of a quaternion from the angle and the axis. Alrighty, that's it. There's my box shape getting made. Function F10. I'm going to step over this. There's my inertial tensor getting made. There's my box, the BGE object, which is going to draw that. You know, it's going to consist of the game component with a transform and a box model attached. So then I call initialize, which is just going to load the model if necessary. That last call is not necessary. And that is also not necessary. Okay, so now I attach the box to the game. Okay, next call is to make the motion state, which is to set the initial quaternion and set the initial position. Before we go any further, it's just an interesting thing. I'm sure you guys have realized this. Function F9. Come on, plus. Look at this. What do you think this API is doing here? GL to BT quad.
Changing from GLM to bullet physics quad.
Awesome. Awesome. Yeah. So, the reason why is because, like, bullet physics engine has its own quaternion class. They're all structs, I think, mostly. But it has its own quaternion, it has its own vector 3, and there's an OpenGL one. They're actually the same, they're just 3 floats. But, you know, to change between one and another, you have to write a function, and this is just a function that I've written to convert from a bullet, you know, an OpenGL quaternion to a bullet quaternion. They're the same, but you still need to convert it to, because this is the type that's expected here is a BT quad, right? That's what that API is doing. So then I make that motion shape, and function F10 here, stepping over, making the rigid body, setting the coefficient of friction, adding the rigid body to the scene. Now create my physics controller, okay? The physics controller takes the box shape, the body, and the motion state. The reason why I passed the shape and the body and the motion state is because if you guys remember, I've constructed these here just using plain old equals new calls. So these aren't shared pointers, these are just ordinary C++ pointers. I need to remember somewhere to free that memory. And that's why I passed it into here, because the destructor for physics controller will call delete on these three things here and free the memory. You know, you don't need to do that in C# or Java, right? But in C or C++, if you allocate memory, for example, in C using malloc, you have to remember to call delete at some stage. In C++, the equivalent is new and delete. Sorry, malloc and free, new and delete in C++. So that's why I just remember those objects, so that when the object gets destructed, I can also delete those other things as well. So there's my physics controller, and then I set a tag on it, which is just a string. And here's a cool thing, which I'm going to get back to next week, called set user pointer. So set user pointer is an interesting thing you can use for ray casting in Bullet. So ray casting just means essentially shooting a ray into the scene and seeing what gets intersected. It's how I implement the gravity one. And you can basically tell Bullet, you know, what Bullet objects are going to intersect with this ray. And you then need to get back the BGE object so that I know like what BGE object that refers to. This set user pointer here takes a void star, so it just takes a pointer to anything. And then when you get the Bullet object back, you can get that void star, you can cast it to be whatever it is. So basically the physics controller is what I pass in as the void star. So at a later stage when I do the ray cast, I get the physics controller back out again. We'll do that next week, okay? So don't get too hung up on it just right now. And then finally, I attach the controller to the box, and then that's my physics object created. So let's hit function to set a breakpoint here in the physics controller. So here's the physics controller, and then I hit function F9 to follow the breakpoint there. Now again, just come back to physics factory, take one quick look at the quaternion, just to remember the position of that object is 5, 5, and 0. So that's the x, y, and z components, 5, 5, and 0. And the object's quaternion is that 0.7 and the final parameter is 0.7. So I'm going to hit function F5, right? When I hit function F5, it's going to get into the update loop. And in the update loop, the physics controller, the thing that's attached to that box, is going to get its update method called, okay? So in actual fact, there's two physics controllers, one for the ground. So I'm going to hit function F5 to let my program run one more time, and then I'll get the box one. So here's the box physics controller's update method called, right? What's going to happen here is, this is going to say to Bullet, okay, this amount of time has elapsed. What's the new position and what's the quaternion? And obviously, because this is just the start of the game, you know, no time has elapsed at this point, right? So this is how you get the position and quaternion out of Bullet. You get it back as this BT motion state object, and you get world transform trans. Okay, you call get world transform, and you get this transform object back. And then I set this guy's set the transform position, convert the Bullet vector to an OpenGL vector, and the Bullet quaternion to an OpenGL quaternion. Basically, when we look at these guys, these are going to be the original ones that I set, you know, because I haven't moved the object. So hopefully the position is going to be still 5. So let me step forward here, function F10. So when I look at the new position here on this transform, there's the position 5, 5, and 0, and there is the orientation. So that's that orientation quaternion there. 0.7, and if you look at the W component, you can see it's 0.7. So what's happened there? Does everyone kind of more or less get the flow here? Created the object, created the BT rigid body. The BT rigid body has, you know, or the physics controller has a BT rigid body. Every frame, the physics controller asks the BT rigid body for its new position and orientation, and uses that to update the object that it's attached to. And that's how basically Bullet links up, or BGE links up the physics rendering with the Bullet physics engine. It's rather complicated, but hey, this is C++. In C++, there's lots of API calls like this. So you get the gist of it.
Yeah.
Create the object, create the rigid body, so on, and that's how it works. Cool, yeah. Like if I was to let this step forward a few frames, like if I go function F5 and let it step forward like 10 frames, and then I get the box one back again, and then I hit function F10, and now I look at the position and the orientation, I should find that the position has been affected by the gravity force. So there's the position now, right? You can see that the x component is 4.9, the y component is 1.9, and the z component is 0 point something. So, yeah, so it has been affected by the force of gravity. You know, the physics engine is basically simulated it a few time steps forward. Yeah, cool. I think it's time for you guys to write some code. You want to take the physics factory code, right, and create some rigid bodies of different shapes. So that you look at the physics factory, you'll see that you can create box, you can create sphere, you can create cap cylinder, you can create from a model as well. So will you just try creating a few rigid bodies using the physics factory and see what happens, and just become familiar with the parameters.
Yeah,